This information is brought to you by Charles Sturt University.
So what we've been looking at is the building blocks of mathematics. So we looked at sets to begin with, and then looked at something that in the first glance seems a bit different. That's looking at true and false stuff, so logic. But as you may have noticed from the rules, the algebraic rules from both of them, they're pretty much the same thing. So they're highly related to each other. The connection is if an element is inside a set or not, really that's true or false. And so at the heart of it, set membership and something being true, a proposition from being true and false, are infinitely related. That's hence why all the rules fall together. And so they're both called examples of Boolean algebras. Which you probably touched on ICC 161, and we'll do a bit more at the end of the subject, okay? So what I want to do is just look a bit more down this idea of the logic path, the idea of looking at proofs. Now, we've actually done lots of proofs already. We have already done them, if anyone put that out. So I just want to look at, just think about how do you do proofs. So most of the proofs we've done so far are called direct proofs, trying to prove them directly. That's not the only way, and sometimes that's not a very good way of trying to prove something, even. So it's good to try to do it indirectly. So I want to talk a bit about that today. So just talk about some terms to begin with, some of the concepts, and then actually going to do some proofs themselves. Just look at the different strategies you might employ. So first word's a theorem. So a theorem is some sort of statement that you can show to be true. That's basically the idea. Theorem is the maths term, but they can be called anything really, like facts, results, laws, propositions. They're all the same sort of thing. And so often how you phrase them is you've got a bunch of premises, a bunch of things, and that lead to a conclusion. So they're normally written as implications. So the word we used yesterday was P implies Q. Well, that's normally what they look like. That's sort of that. And the way we can demonstrate if a theorem's true or not is by proving it. And you've done them at school, commonly for geometry, for example. And we've done quite a few in this subject already. And so they are important ideas. So a common one example at the top there is any rectangle has equal diagonals. So in terms of what we've been doing, the premise of that is we have a rectangle. That's the premise of that theorem. So that's the P. And the conclusion is the diagonals of equal length. Now, I'm not going to try to prove this result or anything like that to you. I just want to see the format it takes. There's a premise, rectangle, conclusion, equal diagonal. And that's often how they're written down. So if you're very computer science, you say if it's a rectangle, then the diagonal is equal. You often say if then. That's how you write code. But English people don't necessarily use those words quite so in the same vein. But that's what it actually really means. It's if rectangle, then equal diagonals. So that's the main idea of a theorem. So a corollary is basically another theorem that can easily follow from some previous result. Normally you don't have to prove them very much because it's just a simple consequence to it. So corollary just really means a consequence. So an example of a corollary to theorem 45 then is any square has equal diagonals. And why that's a simple corollary is because squares are rectangles. And that's pretty much the proof. So if you can prove 45, which is probably the harder yards, then you can easily prove 46 by saying, well, squares are rectangles, the end of the proof. So essentially the corollary is just one more step beyond the main result. So corollaries are just a simple consequence. So other words we might use is the word lemma. So lemma means like a helper result, mini theorem. So they're normally results which people at first glance don't think of being that important by themselves, but are useful to prove something that really is important. That's the main idea of them. So there are some famous lemmas, but you probably haven't seen any of them at all. An example is Euclid's lemma. So Euclid's lemma states if a prime number divides a product, then the prime number divides at least one of those things that form the product up. That's Euclid's lemma. And you go, okay, so that's a result. which are these actually useful in its own right, but what it's really important for doing is being able to say that means you can split up any composite number into a product of primes. That's what they, and that's called the fundamental theorem of algebra, fundamental theorem of arithmetic. And so that's a useful result to prove something bigger. That's the idea of a lemma. So sometimes they're really useful in their own right, sometimes they're not. But that's an example one that you might be familiar with. I mean, you actually know the result. You probably have used it when you factorise things at school, for example. But it's actually true always. Proposition, I use the word proposition. I have used it several times in my notes. It's just another way of saying theorem. What's the difference between the two of them? It's just to say how much. It's just a subjective valuation of how important I think the result is, essentially. So if I use the word theorem, I try to make a bit more force to it. Proposition is a little bit less force. But it's subjective, and people disagree and give different names to it. So most of these things mean the same sort of thing, actually. So lemma, proposition, theorem are all close related ideas. So as I said, most of these things are really forms of implications. And in order to do the indirect sort of proofs, you need to be able to see a sentence and work out what the two parts are. You need to work out what the premise, or premises in general are, and what the conclusion is. And the reason for that is because often, you don't have to write it down using the implication notation on the slide there. You need to be able to recognise the parts so you can do the opposites of one, etc. That's why it's important to figure it out. There's heaps of ways of saying implications. There's a few which I won't go over. We'll just see them when we get to them, pretty much. So just some things is, a normal implication is P implies Q, so the converse of that implication would be Q implies P. So if we think about the little theorem 45 we had was that if you've got a rectangle, the diagonals are equal. So the converse of that would be if you have equal diagonals, you must have a rectangle. That's the converse. The converse is not necessarily true. It isn't necessarily true. And in this case, the converse is not necessarily true. So you can think of it, think hard enough, you can get a trapezium which is equal diagonals. That's something on a rectangle. So the converse is not true. And the way to prove something the way to show something is not true is just to produce one counterexample. So counterexamples can just make a whole theorem fall over quite easily like that. So converses aren't necessarily true. Sometimes they are. When they are true, that's a really interesting thing to do. And so an example of a theorem you have seen from school is Pythagoras' theorem. How would you phrase Pythagoras' theorem? Probably not those sort of words.
A squared plus B squared equals C
Okay,
squared.
so if you've got a right angle triangle, A squared plus B squared equals C squared. So the premise of that is you have a right angle triangle. That's the premise. The conclusion is formula A squared plus B squared. Does everyone remember that result? No one's shaking their head vigorously. That's a few definite odds here and there. So that's the premise, the conclusion. So the converse of that would be if A squared plus B squared equals C squared, that would imply the original premise of it's a right angle triangle. So that's the converse of that result. That is actually true. So what we can say is that those two statements, right angle triangles, one statement, the other statement is A squared plus B squared equals C squared. They're equivalent statements. Equivalent. You can go from one to the other. And so you can think of it as being a double implication, so one implies the other. So it's when the converse and the original result are both true. At the bottom there. And so the way to write that down, like I said yesterday, is if and only if is a common way in mathematics is to say that. So as you can see up here I've got if and only if. So we're not going to do anything with triangles in this subject. Actually getting worried for a second there.
Yeah, my last one.
So Pythagoras' theorem is a nice result for many reasons. But I want to just show you the sort of form, so just picking things you're hopefully a bit more familiar with. So at the end of the day, we need to pick out premise and conclusion. That's the sort of key idea here. Heaps of ways of writing it down. So the way to prove that two things are logically equivalent, so P and Q equivalent, or if P if only if Q, is to prove both implications. You have to prove that P implies Q and the other way around. Q implies P. You have to prove both of them. So just like when you have to prove two sets being equal, you have to say one set is contained in the second one and the second one contained in the first. You have to do both directions. Same sort of thing here. Same idea. So we'll tend to stick with this one. So how do you actually prove things? Just actually, how do you actually go and prove stuff? So theorems, pretty much these little implications. How do you prove them? So the first one is a direct proof. That's actually how we've been doing most of them so far. So this is the basic strategy, plan of attack. So 1, 2, 3 there. So the basic plan of attack is you assume the premise or premises are true. That's where you start from. So what we've been normally doing is we're going left-hand side. Let's just assume left-hand side's right. Let's just muck around with it. Then you do a bunch of stuff, essentially, and that really depends on the context what that means. When you do that stuff, you're doing one step at a time. So when we prove left-hand side equals right-hand side, we did one step at a time to go from the left-hand side gradually. And at the very end, the bottom line, you then want to then show the conclusion is true. So assume the premise, do a bunch of steps, finish with the conclusion. That's a direct proof. And we've done lots of those. So although direct proof is easy to describe, you go, I get what that's all about, well, I hope you do. They can be very difficult to do. And they may not always be the best approach to do it. There's happening one strategy. So let's just do an example. So if you've got n is an odd integer, then n squared is also odd. That's what we're going to try to prove. So that's our result. So let's break it up. What's the premise of this particular statement?
Is it n?
So basically we're given some situation. That's the basic. That's the premise. That's the basic situation.
N squared is odd.
That's the conclusion.
If n is an odd integer.
So that's the premise. So the premise we have is we have an odd integer. That's what we're starting from. That's the starting point, the premise, and the conclusion is that n squared is then odd. So that's the premise, conclusion. So premise is where you're starting from, conclusion where you're heading towards. So the basic approach, the strategy, what we're going to try to do is we're going to assume the premise. So we're going to assume that n is an odd integer. That's where we're going to start from. So we start by assuming the premise. You're going to do a bunch of steps. And at the end of the day, we want to then say, therefore, n squared is odd. So you want to start with the premise, then keep going a bunch of steps till you finally get down to the conclusion. That's the basic way of approaching these things. So all we need to do is just think of what's in between. That's the hard part. So how you do that is you're going, well, it's just one step at a time. So let's look at what we've got. So our premise here is n is an odd integer. So I guess let's write that down as some sort of mathematical equation so we can deal with it. How could you describe n is an odd integer using a formula?
2n plus 1.
Okay, so n is equal to 2, say k plus 1, where k is an integer. And you can say k is in z, like we just said before if you wanted to, but words are fine. So that's sort of a logical step. What do you reckon you do next? Do you think, okay, what strategy? I'm supposed to be getting at the bottom n squared's odd, that's my bottom. So I'm supposed to be doing something to n squared. So let's look at n squared. So what is n squared going to be equal to?
2k plus 1 squared.
Okay, so 2k plus 1 squared, yep. And that's equal to?
4k squared plus 4k plus 1.
Yep, they're okay, expanding stuff. I hope so. So just expand it out. So I go, well, I'm supposed to get n squared is on the bottom, so let's just try it out. So that's my expression. So that's supposed to be odd. That's what I'm hoping to be. How do I show that this number here, that expression there, is odd?
Substitute in a value.
There's lots of values. That could K can be any integer at all. That's a lot of values. It could be. So,
A couple of them. Prove it for K.
That's all I'm saying.
okay, so proving it for 1,000 values is not sufficient. You have to prove it true for every single one of them.
Prove it for K equals 1. And then prove it for K equals some integer. And then prove it for K equals some integer.
Okay, so you can do proof by induction if you wanted to, which is a type of direct proof. And that would work.
Or
We could try something simpler than that though. So what does it mean for something to be odd? We wrote it up here already.
If you divide it by 2, you get a remainder of 1.
So that's really the definition. So if n is equal to 2k plus 1, that's what it means to be odd. Now you can put it other ways, and what you said is also true. So if I could write this down as equal to 2 times by something plus 1, when that thing in the brackets is an integer, it automatically implies it's an odd number. That's our basic definition. That's one we use, so we'll keep with it. So all I have to do is just try to work out what's in the bracket there. So how can I get this to look like this form over here? Well, I've got the plus 1 already, so that's fine. So plus 1's guaranteed. So I just got to factorise 2 out of that first part there. You can see there's lots of 4s, so I can sort of factorise the 2 out. So if you factorise the 2 out, what do you have left?
2k squared plus 2k.
Yeah. And 2k squared plus 2k, well, k is just integer. That's all just gives you integers. So that pretty much says you got 2, give another name, m plus 1. M is an integer. And as soon as you got that, if n squared is 2m plus 1 when m is an integer, that immediately says that n squared must be odd. That's the end of the proof. So, look at the overall strategy. That's the main point I want to get out of it. The overall strategy is start with premise, do a bunch of steps one at a time, finish with the conclusion. This sort of stuff, just thinking, well, what is it? Just go one step at a time. Realising you're supposed to end up with n squared as an odd at the bottom helps you work out that we're supposed to do this step at this point in time, essentially. So knowing what the last line is, so knowing what your overall strategy is, does help to think what the intermediate steps are. Everyone okay with that? Maybe not, but we'll move on anyhow. Yeah, so that's the direct sort of proof. You can do things indirectly. So one indirect way of doing it is to prove the backwards result. And the fancy word to say backwards is just called the contrapositive. So, you know lots of jargon words for all sorts of reasons. Jargon words are used to make a very precise meaning about something. Now, if you don't know what they mean, they just look, you've got no idea. But when you know what they mean, it means something very precise and very handy use definition. And you have lots of terms in computer science for that. So contrapositive one for logic. So if P implies Q, the contrapositive of that is not Q implies not Q. Now those two statements are logically equivalent. What does that mean? If I draw the truth tables up for both of them, the truth tables would be the same. That's what I mean by logically equivalent. So they're the same, effectively. They really are the same thing. And so you could just, and if you wanted to justify that, truth tables would show up to you. So, well, you can use this to make a new strategy. So the basic, another strategy, this is a contrapositive idea, the basic plan to prove that P implies Q is to assume that the conclusion is false. That's where you're starting from. Do a bunch of steps in the middle, and the bottom line you then conclude that the premise is false. If you do that, that would imply that not Q implies not P, and as soon as you say that, that's the contrapositive, therefore P must imply. That's the basic idea. Now, why would you do this? I mean, why would you think of doing this particular proof method rather than the direct way? It just seems to be backwards. The reason why you do this is sometimes if the negatives of both results are easier to deal with than the positives, this is going to be easier to deal with. Let's do an example just to show why you might do these sort of things. Okay. So you've got if n is an integer and 3n plus 2 is odd, then n is odd. That's what we're trying to do. So let's just break it down because we'll need it anyhow. What are the premise or premises in this situation? So what are the things, what's our starting point? What is things, so if we take this directly, what will be our starting point? Top one.
3n plus 2 is odd.
Okay, so we have two things. We actually have two premises. We have that n is an integer and, let's just correctly say, 3n plus 2 is odd. So both of them work together. So bucking them together. What's our conclusion?
N is odd.
N is odd. That's our conclusion. Is the premises. So a direct proof would be to start with saying, okay, n's integer, 3n plus 2 is odd, and then do a bunch of steps to say that n is odd. The reason why that's difficult is because you have to try to divide by 3. And it's doable. You still can do a direct proof here, but it just becomes a little harder. And so actually, an easy thing to write down would be to do the contrapositive. So that's what we're going to try to do. So we'll do a contrapositive proof. And the reason for that is because it's easy to go from something n is odd, something simple like that, to the more complicated expression 3n plus 2. That's why we're doing the contrapositive backwards. So the basic strategy is to assume the conclusion is false. That's the basic idea. So what does that mean in this case? So what's the conclusion?
N is odd.
So what's the opposite of that?
N is even.
Okay, so we're assuming that n is even. That's our starting point. That's our basic strategy. So then we're going to do a bunch of steps. And then we want to conclude that the premise is false. Now, as soon as you say n is even, then n must be an integer, and that's sort of implication for that, so you can't go over that one. So the premise that we have to assume is odd is this one over here, essentially. So what's the opposite of that?
It's even.
Okay, so we have to basically conclude that 3n plus 2 is even. So that's what we're trying to do. So the contrapositive is just doing the opposite. Go for opposite conclusion, do a bunch of steps, get opposite on the premise. And then the cleaning up, I mean, I'll just do the strategy for a moment. Therefore, n is even implies 3n plus 2 is even. If you could do this, the steps haven't done it yet, but that's what we end up proving directly. And the contrapositive, so then we take the contrapositive. So taking the contrapositive of that, so just swap them two around, gives the original result. So that's the strategy. So I want to focus on strategy more than anything else. So strategy, just recapping up, assume the conclusion's false, which means n is even in this case. Do a bunch of steps we get to do. Conclude that the premise is false. In this case, 3n plus 2 is even. And then just a little concluding sentence at the end, just know what you're talking about. And that means I've proved that n is even implies 3n plus 2 is even. Contrapositive then gives me our original result, and I'm done. So that's strategy. Now I just have to work at the details. So let's just think about the details. So we got 3n, n is even. That's what we're starting point. So again, like our last one, we should write a formula down for what that means. Just one step at a time. So just one step at a time. So what is it? What's the formula for n is even?
2k.
N equals 2k, where k is an integer. Okay, so then what are you trying to do? What's our bottom line going to be? Bottom line here is 3n plus 2 is even. That's what we're trying to head towards. So let's look at what 3n plus 2 is equal to. So like we did before, just sub in 2k and so what happens. Sub in 2k, you get 3 times by 2k plus 2. What do we do with that? What would you do next? So 6k plus 2, yep. Then what are we trying to do with this number? What are we trying to do with 6k plus 2?
Prove it's even.
We're going to try to prove it's even. How do you prove it's even? Okay, so you can divide it by 2 cleanly. That would be one way of doing it. There's more than one way of doing it. That's fine. So this is equal to, I can factorise the 2 straight out. I'm sure it's divisible by 2 cleanly. So if you divide it by 2, what do I get?
3k plus 1.
3k plus 1. And so this is equal to 2 times by m, where m is an integer. So you can divide it by 2 cleanly, and that implies it's even, which is what our next line we've already got down there already. And that completes our proof. So similar idea to the last one, the steps. Doing the direct proof there is harder, takes more lines of working. You have to argue indivisible by, dividing by 3 is a bit harder. Unless you start doing mod arithmetic and, who knows how to do mod 2 arithmetic. Yeah, so I thought so. So the maths you know, that indirect proof is much easier. So if you've got mod arithmetic, it doesn't really matter which way, but as written, and that's still the easiest approach to do. So contrapositive. So on the example formula sheet, I've written some of these strategies down because I think it's useful. You need to know them, and I guess that means being able to read them off a piece of paper quickly is sufficient in this case. Okay, so that's one strategy. Another strategy is called proof by contradiction. So this is a very common strategy when doing stuff with mathematics. So it's an old strategy, therefore it's got a Latin name for it, called reductio ad absurdum.
What?
Which basically means reduce to the absurd. So that just shows it's an old proof technique.
Do you get extra points if you write it in the exam?
No.
Is there any like paragraph stuff written in the exam? Is there any like
To write an essay on this proof by contradiction.
seriously?
No, so
That was
an example, an exam question this would be that. So prove that root 2 is irrational using a proof by contradiction. That would be how it would be phrased in the exam. So you actually have to do it. Okay, so pretty much how you do a proof by contradiction, the basic plan is to assume that the premise is true and the conclusion is false. So that's what we're trying to do. So assume the premise is true, conclusion is false, so have both of them together. And then, well, if you think about it, that if the result was true, actually correct, if P really did imply Q, then if the premise is true and the conclusion is false, that means it shouldn't work. It really should not work. So we'll do a bunch of steps, and at the end of the day, we should end up getting a contradiction, which does not work. So now what happens, you should always get things just being completely false at that point in time. As soon as you've got that contradiction, it shows you that the assumption you made earlier is wrong. So the main assumption you made is that the conclusion was false. So that must be wrong. So as soon as that's wrong, the opposite must be true, i.e. the conclusion is actually true, which is what we're trying to do in the first place. So it's just an indirect way of showing that the P implies Q. It's an indirect sort of proof. So why this is useful technique is sometimes the premise is simple and the conclusion you draw is complicated, but the opposite of it is much simpler. So when the opposite of the conclusion is simpler, this is a good strategy. And so last week after the lecture, I was talking about how the set of real numbers is uncountable. So the premise in that case is this: it's got a set of real numbers. The conclusion is that it's uncountable. Uncountable, being phrased negatively, is actually difficult to prove directly. It's actually easier to prove it indirectly. So it's much easier to do a proof by contradiction for that sort of case. Indeed, proving anything is uncountable is easier to do by a proof by contradiction, just because of how it's defined. It's defined negatively. So let's not do that particular one. That's a bit of a harder one. We'll do the root 2 is irrational. So basically, in terms of the underlying logic, P implies Q is the same as saying P and not Q implies false. So that right-hand side there is what proof by contradiction is about. I think it's easy to have a bunch of words on the page to describe strategy rather than just a simple.
Do you think this seems idiotic?
Hmm?
It seems idiotic. Like,
it's a really powerful.
Just because this is true, this is false.
Okay, it might seem backwards. It's a very powerful technique and used in lots of situations. So, and Euclid, who's more famous for his geometry than anything else, certainly used this technique 3,000 years ago to prove things. So it's an old technique, but why it's still around and why it's used back then is because it's a very useful powerful technique. Okay. Okay, so let's look at this case here. Our statement is root 2 is irrational. Just people know what does it mean to be rational? In terms of numbers, I should say, rather than just in general life.
Rational is a simple fraction.
Okay, it means it can be written as a fraction. Irrational means it can't be written as a fraction. That's what irrational means. What's the premise and conclusion of this? Okay, so there is no premise, really. We just have a conclusion. So the premise in this case is true, if you want to go that way, or something like that, just put something down. But it's really just a conclusion, that's all we've got. So we've just got a conclusion. So our strategy for our proof by contradiction, that's what we're going to go to do. So we are going to assume that the conclusion is false. So assume conclusion is false. I'll write it down exactly how I'd normally write it down. So what's the conclusion in this case? Root 2 is irrational. What does it mean for that to be false?
That it is irrational.
Okay, so we're assuming that root 2 is rational. Now, it's good to tell people when you're reading it what you're trying to do. We're going aiming for a contradiction. So basically, the basic strategy is to assume the premise is true and the conclusion is false. And just to make sure everyone knows we're on the same page, we should say we're aiming to get a contradiction. That's what we're trying to do. As soon as you get the contradiction, that ends up proving the result we want to do. So we need to do a bunch of steps, and then we'll get a contradiction. That is really what we're after for. So we're trying to get a contradiction. So basically saying it just doesn't work, something doesn't work. And as soon as we get that point in time, therefore, so if we've got a contradiction, we've assumed that root 2 is rational. So if we've got a contradiction, therefore that assumption must be wrong, must be the other way around. So therefore, root 2 then is the opposite of that, which would be irrational. So it is really going around the the seemingly backwards way of approaching it. So contrapositive and proof by contradiction are both opposite ways, effectively, different opposite ways. Okay, so let's just go through it. So root 2 is irrational. So in order to try to get the contradiction, we just got to play around with it. So root 2 is irrational. Let's write down what that means. So that means that root 2 can be written as a fraction. So P on Q, for example. Don't know what they are, but that's what it means to be rational, written as a fraction. You could keep going on. I know what's going to happen, so I'm going to put something else extra in just to make it quicker. So P and Q have no common divisor. Is an extra thing. So and that's also true. So if you can write it as a fraction, you can make it a simplified fraction. So it was like 2 over 4, for example. You can simplify that to a half. So we can just assume we've simplified the fraction down. And that will help a bit later on. If you didn't put that down now, as you're going on, you go, oh, that's probably going to be useful, and you can put it back afterwards. That's often how you do things in reality. You just keep going, oh, I should have put a bit more up the top here, and I'll just do that now. That's how life works. So now we have no common divisor. So that's our expression. Let's just play with it, see what happens. So we know that root 2 equals P on Q. So let's get rid of the square root. That'll be a good thing. How do you get rid of square roots? Square. So if you square things, you get 2 is equal to P squared on Q squared. I don't like fractions easily. Let's get rid of them. So we get 2Q squared equals P squared. Do you want to cut idea so far? So what can we say? Well, the left-hand side is an even number. Does that make sense? What does that tell you about the right-hand side?
It must be even also.
Must be even as well. So if P squared is even, what does it tell you about P? It's also even. So that implies that P squared is even, and so that P is even. So what does it mean to be even? So that means that P is equal to, say, 2 times by some other letter, 2R, for example. That's what it means to be even. Plug it in and go from there. So if we plug that into our expression, we're getting 2Q squared is equal to 2R all squared. If you expand out, what do you get?
4R squared.
Yep, 4R squared. To a new equation, 2Q squared equals 4R squared. That's what we've sort of got. There's a factor of 2 there. Let's just get rid of the extra factor of 2. If you get rid of the factor of 2, what do you get?
2R squared.
So Q squared equals 2R squared. And if you notice, that sort of equation looks like one we've already got. So this one and this one look almost the same. So we can get the same sort of conclusion. So just like before we concluded that P was even, this time we can get Q is even, like before. Does that make sense? Okay, so we've got basically, so let's just take a step back. We assumed it was rational, wrote down what that means, and then just been mucking around with equations, just what's in front of us. And by going through that process, we realised that P is even and Q is even. That's what we've done both times. But what I did at the top, because I wanted a simplified fraction, I said, let's make it simplified. Let's assume that they have no common divisor. Now, if P and Q are both even, do they have a common divisor? They do. It's going to be 2. So what we can see here is we've actually shown that that all can't be true. There's an inconsistency there. That's a contradiction. So therefore we have contradiction since P and Q have no common divisor. So what we've done, so a thing of the big picture, this is what I want you to do, started with our So root 2 is rational. So we started with our thing, which we the opposite of our conclusion. Done a bunch of steps, and eventually get to a point in time you go, well, that just can't be possible. That's just impossible for it to happen. When you get to that stage, you go, that's the contradiction, which is what we're hoping for, by the way. And as soon as you got the contradiction, that means, well, therefore the assumption we made, the assumption that root 2 is irrational, must be wrong. Therefore, the opposite of that is right. So therefore, root 2 must be irrational, which is what we're hoping to prove all along. So there are more examples in the study guide as well of proof by contradiction if you want to see them. But I think the key idea is you need to identify premise and conclusion clearly, so you can know what to take opposites of. And then when you're doing it, really look at that strategy carefully.
Except when there's no premise?
Yeah, so why did I pick this one rather than any other result? Is I picked something that you might be familiar with, hopefully. So there's a question in the assignment. So if you look at question 3 of the assignment, there's 2 proofs in the assignment, if you looked at that one. Has anyone looked that far down? No, that's fine. We're only just covering it now. So one of them is a proof by contradiction there. And there's a clear premise and conclusion for it. And it's more in terms of the odd even stuff we did in the previous 2. That's the more sort of logic that you require in terms of intermediate steps. But I really want to what I'm assessing you on is your ability to do the overall strategy. So know how to do what the basic the concept of proof by contradiction, which is those sort of steps there, 1, 2, 3. That's the basic overall thing I'm looking for. So you can phrase that sort of stuff down. Okay, so other sort of proofs, so they're the key ones. Other ones are sort of a proof by cases, and that is if you can split the premise into a bunch of different options, so P1 or P2 or P3, etc., a bunch of finite number of options, then one way to do it is to prove it for each case separately. Now this only works if you're proving it for every single case. So it really is written down. It only works if you've got a finite number of cases. Not. So it's easy just to give an example. So if n is an integer, then n squared is either 4k or 4k plus 1, where k is an integer. So why is that useful? It shows you what sort of form that a square is, so you can use that in number theory to work out, eliminate some numbers not being squares, etc. It also has other results in number theory resulting from that. So it's a lemma, as in it's a help result, which at this point in time doesn't quite seem clear why you'd ever use it, but it is actually a useful result. So what's the premise of this result? So what's our starting point? N is an integer, that's it. So our premise is n is an integer. The conclusion is
n squared equals 4k or 4k plus
1. Okay, so n is 4k or 4k plus 1. For some integer. So that's our premise and conclusion. So it's easier to do. So you can see the conclusion has 2 parts to it. So it's either 4k or 4k plus 1. So you're going, well, why don't I just split up the premise into 2 different cases? One case is if n is even. The other case is if n is odd. If I can do both of them separately, and that gives me a result. So if I can say, let's assume for the moment n is even, do a bunch of steps, and then show therefore n squared is one of those 2 options, that proves it for the even case. If I then say if n is odd, do a bunch of steps, and then say n squared is one of those 2 options, that proves it for the odd case. And proving for both cases separately then proves it for the whole thing together. That's the idea of proof by cases, doing both the 2 cases in this situation separately. It is, yep.
It sounds like someone's doing a...
It's taking a snapshot of the screen, that's what it's trying to do.
It really sounds like someone's having like a limb chopped off.
Have you chopped all the limb off?
Well, that's super detailed.
Yeah, that's very specific.
Okay, so case 1. So case 1 is n is even. That's our premise. So that's the premise for the first case. We're trying to do a bunch of steps to show that n squared is equal to either 4k or 4k plus 1. Alright? What does it mean for n is being even? What's the formula for it? So n is equal to
2k.
So k is used up here, so I'll use a different letter. So m then, yep. So n equals 2m. M is an integer. I want to know about something without n squared, so let's square it. So n squared would be 4m squared. Therefore, n squared must be equal to 4 times by, call it k, which then proves it, essentially. That makes sense? That's exactly what we're trying to do. That's our conclusion. So we proved it for case 1. So, as desired. Let's make it clear what we're trying to go for. So we started with case 1, we started the premise, done a bunch of steps to get at least part of that conclusion. So n squared equals 4k, where k is an integer. That's what we're trying to do. That's part of our conclusion. Case 2 then would be what? What's our second case?
How did you get rid of the square root on the m? You didn't do anything to the left. Oh, okay, right.
M squared's just an integer. Let's just call it something else.
Yeah, it all makes sense now.
Just give it another name. That's all it is.
Right.
Case 2 is the same thing. Really, it's the same idea. So what's how do you rail it off to me? What the other side looks like?
N's odd, so n equals 2n plus 1.
Nod. It's even spelled different.
Okay, so we started with the premise that n's odd. That's our premise for our second case. Do a bunch of steps, similar sort of ones as before. Our conclusion is that n squared is equal to something or other. That's going to be the conclusion we want to draw. So let's just do that. So we want to consider n squared. What's n squared going to be looking like?
2m squared plus 2m plus... wait.
So 2m plus 1 squared, which is you're saying to me...
Squared plus 4m plus...
Is that sort of form? We wanted to make it look like either 4k or 4k plus 1. Which of those two cases do you reckon it's going to be? Okay, it's going to be the 4k plus 1 case. So we'll make it 4 something or other plus 1. That gets it in the form we would like it to be, one of those two options.
Put k there.
So that's equal to, so 4k plus 1. So I'm going to say that. So let k equals
Who cares?
the middle part there, and we can see that n squared equals 4k plus 1.
K equals...
Which again is as desired.
K actually equals k.
And then I'm running out of room, but I would write one more sentence down, I think. So therefore, whether it's for odd or even, it shows you that the conclusion is true in both cases, therefore we've proved the theorem. That's the idea of proof by cases. And you can see they sort of mirror each other. Any questions with that? So it just mentioning something that we already alluded to, you can't prove something by just giving a bunch of examples. Just a few examples doesn't prove things. It might suggest it's believable, but it doesn't prove it. So as an example is theory 56, all odd numbers bigger than 1 are prime. So I can give a bunch of examples. So 3, 5, 7, 11, 13, they're all examples that satisfy this result. I can give an infinite number which satisfies this result, as a matter of fact. But that doesn't prove it. Why can't I prove it?
Because you can't do all of the numbers.
Nine's not.
Okay, so it's not true is the reason I can't prove it. And the reason is because 9 doesn't satisfy the result. So I can disprove something very easily with using one counterexample. So a counterexample is 9. 9 is an odd number, but it ain't prime.
That's like a terrible kind of thing where it's like, the new Ghostbusters movie is terrible, but there's one review that says it's good, therefore you can't say it's terrible. It's like the same thing. It's ridiculous.
Okay. So we're talking about true false statements.
Yeah, I know. It's good.
So
let's go in between.
I suspect that in terms of what we're doing is good and bad is not a discrete set, it's probably more a continuous variable in reality.
I don't know.
So it isn't just true or false, it can be a whole spectrum of things. Which is why you can't apply exactly the same ideas in that situation. So you can't prove by examples. You have to try to prove for all instances. So if you're going to prove this properly, you have to consider all lineages. And as soon as you try to do that, you realise it's not going to work. So the next thing I want to do is, I'm not going to do right now, the last proof technique I want to cover is the idea of reduction, which is what you mentioned a second ago. So we'll do that in our next lecture. And so induction is also an induction question in your assignment. So pretty much from what you can do now is you can do anything in the assignment 1 except for the induction question. And it's very clear because it says proved by induction, so that's when you can't do just yet. But you can do the rest. Now, maybe you can, depending on what level of maths you do at school, you might be able to do it. So just as you pack up, who has done induction before?
I know about it.
I'm pretty sure.
The answer is if you don't know what it means, the answer is you haven't done it before.
I've done it, but I don't like the induction.
Useful. Meaning it's funny, but
The whole exam is worth 3 marks, and it's a whole page of work.
okay, I'll see you guys in tutorials at 12. 12 upstairs, 4:16.